Hello everyone, Mr. John here, and I want to welcome you to our kind of live number theory problem solving session. So hopefully everybody can hear me okay, see me okay as it's popping up here. And so just want to welcome everybody for our final one of this series this week. Right, we did some word problems, so it's some pre-algebra stuff. We did some geometry, we did some counting and probability, and today we're going to look at some number theory questions. So hopefully people are doing well. I just want to remind everybody, let's try to keep the chat, so reminders, stay focused in chat, right? And we're here to solve math problems, right? So we'll have a couple easier problems, warm-up questions at the beginning, and then do some slightly more difficult ones along the way. So even if you're finding them easy, even if you're finding them hard, right? That's okay. Everybody's on their own level, and that's kind of great as well. So yeah, we will kind of get started then right away. And I have a few warm-up questions right off the bat that we can think about together, and we'll kind of go over them. I'll kind of go over them this way too. So first question, this is from old ZIML Division E, so pretty straightforward if you're a little bit older as well. Tina visits her mom every 2 weeks. Her sister Tara visits her mom every 3 weeks. They both visited their mom this week, right? So Tina and Tara just saw their mom this week. How many times would both of them visit their mom in the same week during the following 15 weeks? So, right, we have some kind of easy ways of approaching this. Just as it's kind of our warm-up question here, I want to quickly go through a little bit here with how you could start visualizing this. Of course, we don't want to actually do this all the time, right? These are just to help us start seeing patterns and stuff like that as well. So for Tina at least, right, we have a 2, 4, 6, 8, 10, 12, blah, 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 right? These are all the dates that Tina is going to be visiting her mom in those weeks. So let me spread out the Tina and Tara a little bit here. And then we could make the same list and do that for Tara, right? So it's of course not the same list, and I'm going to have to squeeze some stuff in here, right? So Tara 3, 6, 9, 12, and then 15. Okay, so here then, what do we want to notice? We want to notice this 6, right? And so people are pointing this out in chat. That is great, right? So every 6 weeks, we actually have them visiting, right? Because kind of 2 times 3 equals 6, 3 times 2 equals 6. This is the least common multiple, right? We'll talk quickly about these, but I think a lot of people know these, right? LCM of 2 and 3 is 6, the least common multiple. And so that means every 6 weeks, they will see their mother together. So weeks 6 and 12 and 18 and 24 ... work. Answer is 2, right? So does the 15 really matter, right? Is this question any harder once we understand it if it was 150 weeks, right? Not really. So once you have that LCM idea, you should be in kind of good shape from there. That's kind of perfect as well. Okay, so next warm-up, right? Second warm-up here. How many perfect squares are there between 150 and 650? So this one is, right, just a little bit of vocabulary as well. So just to remind us, as people are kind of answering the question, I'm sure this one's pretty quick as well. Just as a reminder, a perfect square means, right, the number, or let me just say it this way, n is a perfect square if n equals k squared for another integer k. So we can kind of write these out as something else squared in this case. So sometimes this will just be called a square, right? Sometimes to just denote, right, that it's actually exactly a square, you'll see the word perfect thrown in there as well. So we have perfect square from there. Now, this is in some ways a counting question, right? So this is kind of what we have from last time. And it's a counting question, but also a little bit of arithmetic too, right? So we have 169. So where does this 169 come from? So other people are mentioning this in chat as well, right? 13 squared, right? So 13 squared is 169, is the first square, right? So this is just practicing some of your kind of arithmetic a little bit, right? 13 squared, 14 squared, 15 squared. Of course, again, you don't need to calculate all of these in this case. Now, I'm going to say 26 squared. What is 26 squared in this case? So can anybody tell me what we have for that kind of value as 26 squared? Or if you want to be lazy and tell me something slightly different about 26 squared, that is kind of fine as well. So maybe if we want to be a little bit lazy here, right? What's important about 26 squared is it is too big, right? So really here we can say 25 squared, which as mentioned before is 625, right? So we're counting then, this is the last square. So then we have 13 up to 25. Don't make the silly mistake there. Remember, how do we kind of do that, right? So it's 13 to 25. Then that means we do 25 minus 13 plus 1, right? We don't want to disclude actually 13. And so you get a final answer of 13 in this case as well. So that's good, right? This is another good quick warm-up question talking about some vocabulary and things like that as well. Okay, so what do we kind of talk about then when we're talking about number theory, right? So how do we in general kind of solve a number theory question, right? So remember here, a lot of these things are dealing with integers, right? When we say number in a number theory question, even if it's not going to be always like that, right? We're talking about numbers, we're talking about their digits, we're talking about prime factorizations, kind of things like that as well. So remember here that kind of a prime number is one that only has factors of 1 and itself, right? Greater than or equal to 2. So we have 2, 3, 5, 7, 11, right? 13. These are useful things to know. So of course we read a question carefully, but one of our biggest helps for almost every number theory question, of course not all of them, but almost every number theory question, these prime factorizations are going to be a good place to start. If you're stuck with a problem, prime factorizations will help. We also have divisibility rules, right? We talked a little bit about greatest common divisors, least common multiples, and then patterns. So we already saw some patterns of things before, but just kind of want to remind us the other place patterns come up all the time are questions like find the last digit of blah, 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 or, right, find the remainder when blah, blah, blah. So these are some of those common questions that we'll be talking about in terms of patterns. So they're really remainder questions, or if you're more advanced vocabulary-wise, modular arithmetic a little bit, but they mostly boil down to patterns that way. I want to do a quick review of these things just to kind of talk about them a second. So first of all, prime factorizations again. Like I said, these are one of the most important things when we're talking about number theorem. Every number can be uniquely written as the product of primes. This is obvious that you can write every number as primes because you just keep breaking it down. And you have to stop eventually. Otherwise, how would you keep going forever? The numbers are getting smaller as they're being broken down, so you have to stop at some point. It's not actually obvious that it's unique, right? But it is. So that's a little bit more of an advanced topic, but if somebody factored it using one factor tree, you factor it with a different factor tree, at the end, no matter what you do, as long as you do it right, at least, you're going to get the same answer in terms of the product of primes. So, how are these useful? You can find the factors, you can see what types of factors you have, you can find the number of factors. You also can use these for the GCDs and the LCMs, right? GCD, greatest common divisor, also greatest common factor. Those are synonyms in this case. So you're kind of fine either way there. Now, right, how do we do this number of factors? I want to kind of make sure everybody is okay with the number of factors trick. So the number of factors trick is, right, if we have 2015 here, so this is 5 to the first power times 13 to the first power times 31 to the first power. So what is our trick for the number of factors? Right, so you take all the exponents and then you add 1 to them. So every exponent plus 1, and then you multiply out. So here, right, where does this 8 come from, or where does this 2 plus 1 come from? Right, this 2 plus 1 is really a 1 plus 1 for the 5. Right, so we have the exponent plus 1, 13 plus 1, 1 plus 1 for the 13, and then 31 is a 1 again, so 1 plus 1 there. So that is giving us our 8 for this trick for calculating the number of factors. Yep, that's exactly right, kind of as explained in chat as well. We'll see another question, or actually a couple questions, just practicing this real quick in a little bit as well. But this is a very, very useful and very helpful thing that way as well. Now, the other thing that definitely we want to review, or just you want to be reminded exists if you already know this, which I'm sure a lot of people do anyway, right? We want to talk quick about the divisibility rules of numbers as well. So these all are rules involving the digits, right? So these rules here all depend on the digits that we're talking about, right, when we write the number, depending on the place values and digits, right? So every number could be written as primes, but another way of breaking it down is writing it with its digits, right? 2019 is 2000, 0 hundreds, 110, 9 ones. So everything could be added up that way as well. So for numbers like 2 and 5, this is just the last digit, right? Is the last digit divisible by 2? Is the last digit divisible by 5? If you're talking about a number like 4, you need the last 2 digits. So all of those kind of things are fairly simple in terms of that last digits. Why do those work, right? Because we're working in base 10, right? So if we talk about 2 and 5, 2 and 5 are both factors of 10. 4 is a factor of 100. So those other digits after that point don't matter. So have people kind of heard rules for kind of the sum of the digits, right? 3 and 9, and the alternating sum of the digits, 11 as well? Yeah, so a lot of these are good too, right? So let's just do kind of a quick example here, right? So for example, if you have the number here 1113, the sum of digits is 1 plus 1 plus 1 plus 3 equals 6. So it is divisible by 3, but not by 9. So this kind of is a good rule for kind of 3 and 9 in this case. So these are kind of our sum of the digits here. Does anybody know the rough idea why this sum of the digits works? What is the kind of rough idea here? Again, it's going to kind of involve 10, but you want to think of sum because, right, 10 is 9 plus 1. And of course, 9 is 3 times 3. So this is kind of where this sum of the digits roughly comes from. Of course, you need a little bit more care when you're doing this for kind of stuff like that as well. Now, alternating sum of the digits, there's different ways to do this, but a good way, and the way I would recommend because it has some nicer properties that help you out later on, if you want to actually not just worry about a rule, but worry about kind of divisibility and remainders as well, right? You do the numbers, right? Do plus minus from right to left with the digits. So let me kind of do an example here for this one. And this way might be a little bit different than you might have seen this in the past. So that's where I want to kind of think about it this way as well. And so if we do a quick example here on the bottom, right? So for example, 1, 2, 3, 4, right, has alternating sum 4 minus 3 plus 2 minus 1 is equal to 2. So it is not divisible by 11. So this is what we kind of have there as well. Okay, so yeah, so there are some rules for other things, right? So in chat, we're having a discussion a little bit about 7. You might also wonder about kind of 13, things like that. A lot of those other ones are a little bit messy. I would say these are the most important ones to remember and use and stuff as well. Do ones exist for other things? Yes. But these are kind of the most important ones that are really practical and really help you out a lot. Why do I kind of say that as well? Don't ever forget that you can just always use nearby multiples to help you out, right? For example, what if you want to know the number, if the number 500 is divisible by 7, right? So other rules exist, but are kind of not super useful. So remember, you can always go back to basics. Remember, basics can be helpful too. So, for example here, what if we want to think about, is 500 divisible by 7? Is 7 a factor of 500? Well, what could we do that's close? Can anybody tell me what 7 times 70 is equal to? Well, 7 times 7 is 49, right? So this is 490. So 490 plus 7 is 497 is a multiple of 7. So 500 is not, right? So these are some things that kind of are pretty helpful a lot of times when you're doing some other numbers or things like that as well. So this kind of is how you could kind of think about stuff that way too. Okay, so let's move on then to do some questions. We're kind of all good with our basic rules here. And of course, reminder again, all of these problems are coming from ZIML, so Zoom International Math League. Hopefully everybody can get a chance to check out this site for just some free practice problems and stuff like that as well. Okay, so let's look at some of these problems here too. So first question is not so difficult, but again, we can just practice it quickly here. How many numbers less than or equal to 1,000 are multiples of 45 and 75, but not 18? So a lot of you guys can do these things in your head, but I want to use this problem to kind of remind us okay, so remind us of how you could do this with showing some work and kind of explaining how it works with a lot of these other pieces of information as well. So 45 is 3 squared times 5, right? It always is, remember I said a good place to start for a lot of these problems is prime factorizations. So we have 3 times 5 squared for 75, and 18 is 2 times 3 squared for that as well. Okay, so this kind of is all of our setup here. And now, what does this allow us to easily find from here, right? This is where the power of the prime factorizations can be helpful. I know a lot of you guys are good with these small numbers for how to do this, right? But what then is the GCD of these two? So the GCD of 45, and maybe let me just type this here. The GCD of these two numbers then is equal to 3 squared times 5 squared. So this is 9 times 25 is 225. So yes, of course, you can just calculate that directly as well, but that's kind of good to think about there. So as soon as we see that 225 in this case, oops, yep, and I made a mistake there too. This is not the GCD. This is the least common multiple, right? Because we're looking for factors of both of those there. Yeah, so 225 here. So as soon as we have that, we can be thinking about, okay, what are the numbers we have? We have 225, then we have, right, doubling that, 450, then we have another 225, 675, right, and then we have 900. So we start off here with 4 numbers that are less than 1,000 and are multiples of 75 and 45. But, right, we want to say, but not 18. Right, so we also have to look about this, but not 18 there. So you could, of course, just check the 4 numbers, right, and then just cross out those ones there. But I want to kind of just quickly point out here too, this is actually another LCM, right? So if we calculate the LCM of all 3 of them, we can do this the same way. What's the power of 2? We need at least 1 2. We need at least 2 3s. We need at least 2 5s, right? So this is 2 times 3 squared times 5 squared equals 450. And so then that allows us to go down and cross out all of the ones we do not want. Cross out 450, cross out 900, and we're left with 2. So yep, everybody's saying earlier, answer is 2. You guys are all correct. That's good as well. Okay. Yep, so this is what we have for the problem here. And again, why are the LCMs important and kind of knowing how to do that, right? Remember, you always want to be able to extend this question into a harder question. right, you can use this same exact procedure. It's messier, but if I change this to something like, right, 450, right, 750, 180, this is pretty much the same, right? But if we do 450, 750, 180, and we want to do numbers less than a million even, you have a set procedure you can use to solve that question there. So that's kind of what I want to make sure we're kind of comfortable thinking about in that case as well. Okay, so yeah, let's look at this one next here. This one is a good one to do a couple of practice things with. Okay, so Claire wonders how many factors the numbers 2019, 2020, 2021, 22 all multiply together. So here we have a little bit of difference in terms of multiplying them all together. And we want to know the correct answer to this question. Now, really the reason I wanted to go over this today is that, right, knowing the prime factorizations of recent years is very helpful. Now, why is this helpful? Well, they show up a lot on questions, right? If you're creating a math question a lot of the time, it's hard to decide on what number should I use, right? Well, oh, it's the year 2020, and so then let's use the number 2020. Now, why is it helpful to memorize these things, right? Why is it good to know these, right? It's important to know, right? Good to know because some are very ugly, right? Prime numbers don't have to work out very well. Yeah, so other things are good to know. Yeah, so factorials are good to know, right? Some basic stuff about choosings or things like that. But yeah, in terms of the number theory stuff here, these factors are kind of pretty easy to know as well, or good to know as well. And so some of these are kind of a good example right away. So what about 2019? Does anybody know the prime factorizations? And we can just open it up to all of them so we can help each other out here. We don't need to do them all totally together. I want to just start by listing out all of these prime factorizations here, and we can kind of go from that. So 2019 is 3 times 673. I agree with that one. A lot of these other ones are even, right? So those are kind of a little bit straightforward. Half. Okay, so what about 2020? So this one is a pretty easy one here as well. So 2020, of course, is divisible by 20, which is 2 squared times 5, right? And then we have 101. 101 is definitely a prime number you should know. 2022 is 2 times 3 times 337. Now, my hint for 2021, and I'll erase this in a second, but hint for 2021, it is not prime, and it is about as bad. It is like the worst case in terms of factoring there. So what do I mean by worst case in terms of factoring, right? How do you know if a number is prime? Well, you check. Is it divisible by 2? Is it divisible by 3? Is it divisible by 5? Is it divisible by 7? Is it divisible by 11? 13, 17, etc. As a more of a hint for 2021, 2021 is not divisible by any of those numbers. So what is the last prime? So to check whether 2021 is prime, you have to check all the primes up to what? Does anybody know the kind of trick for how long you have to keep going here? Right, so is everybody kind of okay with this rule, right? So if you check a number as prime, you really only need to do the primes up to the square root, right? So you can go up to the square root of 2021 here. And so that's in the 40s, right? Somewhere in the 40s. And yeah, in fact, people have got this in chat now. That's good. This is worst case in that it's multiplied by the two primes, 43 and 47. So that's kind of the two primes right next to each other in this case. If you know some algebra, in fact, that means kind of this, is like a 45 plus 2, 45 minus 2, stuff like that there as well. Okay, so now we're just in a place where we need to work carefully and apply our rule, right? So the full number then has prime factorization, right? We just combine all of our rules here as well, right? So this full number, what is its prime factorization? Well, we have how many 2's, right? We have 3 2's. How many 3's do we have? We have 2 3's. We have 1 5. Then we have a 43 and a 47 and a 101 and a 337 and a 673. Okay, so please let me know if I mess this up. And hopefully I did not mess it up there. But just let me know if I'm missing any of them, right? So the number of factors is 4 times 3 times, and then a bunch of 2's, right? 5, 43, 47, 101, 337, 673 here. So this kind of is all of our different ones there. And let me kind of just double check this quick here. And yep, okay. So I got the right answer, so I'm a little bit more confident then in the steps along the way as well. So as people wrote out earlier, right, 768 is the factors here. Yeah, so 768 should be good in this case. Now, it's not relevant for this problem, but there's actually one other very good number you should have memorized in terms of the prime factorizations. So can anybody tell me what is the prime factorization of 101? 1001. Now, 101 is prime. 1001 is not prime. But what do we have here for the prime factorization of 1001? So good. This is 11 times 7 times 13. So this one is very useful. So people were asking before a little bit, what's the rule for 7, right? There's not really a super nice rule for 7. There's not really a super nice rule for 13. But one kind of fact you can think about here is that if you multiply these numbers together, you get 1001. So that can be kind of helpful in a lot of cases as well. Okay, so let's do one more of these in terms of prime factorizations. This one again is not too difficult, but I just want to make sure we understand how to use prime factorizations in this case as well. So, okay. So how many factors of 30 to the 10th are perfect squares? Okay, so 30 to the 10th power. Of course, we can just break this down, right? 30 itself has a prime factorization, and then we can go from there, right? So 30 is the same as 2 times 3 times 5, right? So 30 to the 10th power is equal to, right, 2 to the 10th times 3 to the 10th times 5 to the 10th power here. Now, is this question much different then, or this is kind of a good testing of, do you really understand the prime or the number of factors formula, right? So how many factors does this number have in total? This number has in total then, of course, 11 times 11 times 11, right? It has 11 cubed factors there as well. Now, what has to be the case for a number to have a perfect square as a factor? Or just in general, what do the prime factorizations of perfect squares look like? Does anybody know kind of the pattern or how kind of things look in terms of, right, the prime factorization of a perfect square? What kind of happens for those numbers? Right, so this is related to some other facts that I'll kind of type out in a second here too, right? So related fact that's kind of helpful. Only perfect squares have an odd number of factors. So that kind of is related to this in a very real kind of way as well. So, right, if we're thinking about what do the prime factorizations look like, everybody know that it has to have all even exponents there, right? So what is kind of the reasoning for that? Right, the reasoning for that is, right, we're just kind of talking about, right, even exponents because we have squares, right? So what's the square root of 5 to the 4th power? It's 5 squared, right? So you can always, as long as you have even exponents, those are kind of things that are good to think about there. So, okay. So here we need to be a little bit careful. I don't think I've actually seen the correct answer in chat quite yet. So I think we all agree, right? Any factor of this number is 2 to the something times 5 to the something times 3 to the something, right? So any factor here is 2 to the something, right, times 5 to the something, 3 to the something, so each blank must be even. And what's the other fact here? So let's be a little bit careful. So 125 is getting close in a very real sense. It's still not correct, but it's close. So each blank has to be even, and each blank can't be bigger than 10, right? So each blank also has to be, right, less than or equal to 10. And what though, right? Let me say, right, from 0 to 10, right? greater than or equal to 0 and less than or equal to 10. So each blank has how many choices? Thus, each blank has 6 choices here, right? So that's kind of one thing we want to kind of be a little bit careful with, right? 1 is a perfect square. The actual number itself is a perfect square in this case, right? So we have kind of different pieces we want to be kind of thinking about for this problem. So, right, then if we put it all together, there's actually 216 factors here, right? So we have 6 times 6 times 6 equals 216 in total. So that's what we're going to get as our final answer here. Yeah, so I think a lot of people were on the right track along the way, but we just kind of want to be a little bit careful with some stuff there as well. Okay, so let's try to do 2 more questions quick. We're getting kind of closer towards the end here, but I want to for sure do one divisibility question and then hopefully one of these pattern questions as well. So we have for this problem, we have 2 5-digit numbers. We have a 5-digit number 1A2B3. It's divisible by 9. So right, the key thing here is that whenever we have missing digits, we want to maybe label them by a letter. Now, other thing here, the line over the top is just kind of talking about the digits, right? So 1A2B3 means the 5-digit number with 10,000 digit 1 and right, thousands digit A, stuff like that. Okay, so what then do we have for our other 5-digit number? We know that this number is divisible by, whoops, I'm having one extra number there, so let me delete that. I want this to be 11, so that should be good now then, so sorry about that. Right, we're just practicing our rules for 11 and 9 with this problem. Now, do you guys think we should start with the first number or the second number? Which number is probably better to start with for this problem? Well, you can kind of think about this in terms of how many missing kind of variables or digits are there, right? So you could do either way, it's fine. But I think it'll be better to start with the second one because that only involves A, right? So let's start with second because only A is involved, right? So what can we say for this second one, right? 11, so we use, or let me say, divisibility by 11, so use the alternating sum of digits. So what do we have in this case? We have 6 minus A plus 5 minus A plus 4. So this is the same as, right, 15 minus 2A in this case. So what does 15 minus 2A have to be equal to? Remember, this can actually be equal to infinitely many things here, right? This could be 22 or 33 or negative 121, right? But a lot of those don't make sense, right? So what are some possibilities here, right? 11 or 0, right? Things like 22 or negative 11 don't work, right? We can just kind of focus on the ones that we have or we're kind of thinking about in this case. So from that though, does 0 work? Actually, no, right? So in fact, from this first one here, we can literally tell us what A is equal to, right? So this tells us that A equals 2. So we have kind of our equation there, and then that gives us a value of A. And then, yeah, I think people are on the right track repeating this for the first number, right? For the first, we can now use the divisibility by 9. So we use the sum, straight up sum of the digits in this case. So we have 1 plus A plus 2 plus B plus 3. Wait, we know A is 2, so that is just 1 plus 2 plus 2, 5 plus 3. This is B plus 8. And so then this could be equal to, right, 9 or 18, right? Or just actually 9, right? Things like 9, 18, or 0 don't work. And so then, right, this allows us to figure out what we have as our answer then in this case. So, right, this tells us that B is equal to 1, as a lot of people were not mentioning, but a lot of people were mentioning the final answer, which is good as well, right? Answer is 2 plus 1 is 3. So that's kind of great there as well. Okay. So that's maybe a good place to stop then for today. I guess we're actually at our time kind of here, right? So let me just kind of go back to the kind of ZIML page here just so we can kind of end seeing that, right? Again, recommend you kind of go there. Yeah, it's a free account to get started, so you just need to kind of create a quick account either on the site or on the app, and we have a lot of kind of free resources and other things for you guys there as well. Okay, so also want to end as usual, right? Stay safe, everybody. Thank you guys for joining me today. I enjoyed working with everyone on some of these problems today, right? Hopefully everybody has a good weekend and kind of things are not too kind of crazy. We might have some videos again starting next week, but maybe for the next time we might have just a recording video. This is going to be the main one in this kind of series and stuff as well. So I recommend kind of looking at that ZIML site. There's some more kind of problems there. And then we'll keep posting some videos or some other things on the YouTube site. But for now, at least, we're kind of still deciding what we're going to do kind of moving forward. So hopefully we see you guys trying some of those free problems on ZIML, and we'll have some other activities and stuff there as well. So tentative plan is we'll post another video on Monday. Maybe not a live video, but hopefully we'll have something for you guys to go on our YouTube channel and kind of watch later on as well. But thank you guys again for coming right now. And I will see you guys all hopefully in the future that way as well. So have a good day, everybody. Have a good weekend. Goodbye.